And the short ones, you can figure out from, these are all 20 degrees, 400, 620. Okay, so this is tension compression. Number 4. And it looks like this. And all these angles are 20 degrees. And we have a 400 Newton force and a 620. Okay, and I'm going to label these. I'll call that 1, 2, 3, 4, 5, 6, 7. So we're going to be trying to solve for 7 variables. And let's label the joints. So A, B, C, D, E. And let's just start with pin A. We have a reaction force from the ground. And we have a tension force F2 and a tension force F1. So Newton's second law says RAX, RAY plus, this is at an angle of 20 degrees from the x-axis, so that's 0.940 F1, 0.342 F2, no, F1, sorry. We're just multiplying the unit vector times, so I'm just multiplying the unit vector 0.940, 0.342 times the magnitude F1. And then we have F2, 0. Okay, so that gives us our first 2 equations. I guess I'll rewrite this. So we got RAX plus 0.940 F1 plus F2 equals 0. And our second equation says RAY plus 0.342 F1 is equal to 0. Then we'll go to pin B. The force is here. We have the 400 Newton force. And then we have F4. And then we have F1. We had that before, but remember, we're assuming that these are in tension, so this is going to be going the opposite direction on this pin that it did on pin A. So this is F1, and then we have F3. Any questions about that free body diagram? So now Newton's second law, let's see. Horizontally, we have, it never hurts to just write these out as vectors and then rewrite them, but I'm going to just jump right to the equations to try to save a little time. But we have negative 0.940 F1 plus 0.940 F3 plus F4 is equal to negative 400. And equation 4 says negative 0.342 F1 minus 0.342 F3 is equal to 0. And then pin C, so we have F2, F3, F5, and F6. I said that we're trying to solve for 7 variables, but that's not true. Well, the only ones we if we could solve for just 7, we'd be happy to do it. But we have 10 total because we also have this reaction force vector RA at A and a single value at E. Okay, so Newton's second law here says negative 0.940 F3 plus 0.940 F5 minus F2 plus F6, bless you, is equal to 0. And then positive 0.342 F3 plus 0.342 F5 is equal to 0. This is equation 5 and equation 6. And now pin D. We have the 620 newtons acting down. F4 that way. And then F5 and F7. So negative F4 minus 0.940 F5 plus 0.940 F7 is equal to 0. And then equation 8, we have negative 0.342 F5 minus 0.342 F7 minus 620 is equal to 0. So I'll write this as equal to positive 620. One more to go. So the pin at E we have F7, F6, and then this is a roller, so we know that's acting straight up, and I'll call that RE. So Newton's second law says F6, negative F6, minus 0.940 F7 is equal to 0. And equation 10 says 0.342 F7 plus RE is equal to 0. Okay, so now we have 10 equations for 10 variables. Whoops. 1, 2. Okay, so here's my augmented matrix now. We have 10 equations, so we need to have 10 rows. So there's equation 1, equation 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have 10 variables. I'll write it as RAX, RAY, and then RE. To this? Sure. F1, F2, F3, F4, 5, 6, 7, and then a column for the constant. Okay, so for the first equation, can someone read me the values here and I'll enter them in? So just equation 1, we have 1 RAX. F1, we have 0.940. What else do we have in equation 1?
1, 2.
What?
2 is 1.
Okay. And that's it? And then equation 2?
1 F1 already one.
Okay.
0.342 F1.
Okay.
0.
Okay. F3, equation 3.
F1 is negative 0.940. F3 is 0.940. F4 is 1. And then a constant of negative 400.
Okay. Equation 4.
F1 is negative 0.342. F30 is negative 0.342. And then zeros.
Okay.
Equation 5, F3 is negative 0.940. F5 is 0.940. F2 is negative 1. F6 is 1.
F2 is negative 1. F6 is 1.
Yeah.
Okay.
Equation 6, 0.342 for F3. 0.342 for F5. And that's it.
Okay.
Equation 7. We have negative F4 or negative 1 for F4.
Okay.
Negative 0.940 for F5. 0.940 for F7. And that's it.
Okay.
Negative 0.342 for F5. Negative 0.342 for F7. And then 620.
Class 2.
Negative 1 for F6. Negative 0.940 for F7.
Okay.
And then 0.342 for F7. And 1 for R8.
All right.
Remember that one? 1560. Yeah, like 2 days.
Yeah. Okay, so here's what I got. Tell me if yours match. Or tell me if they don't match, I guess, because, so RA, I got negative 400, positive 118.62. Yeah?
Yeah.
Yay. And then RE, 501.38. F1, negative 346.83. F2, 726.02. F3, 346.83. F4, negative 1052.05. F5, negative 346.83. F6, 1378.07. And F7, negative 1466.03. Yay. Well, so that member 7 is really having a hard life. So this member 7 is in compression with a value of 1466 newtons. The second biggest absolute value of load is 1378 for F6. So this one's in tension, this one's in compression. All right, and then what else does it ask us to do?
stress tensor for each member.
But it doesn't tell us a cross-sectional area. Okay, well, so so the cross-sectional area for each one let's say it's a square cross-section of 1 centimeter. And so the area is 1.0 times 10 to the minus 4. So now you can go through, you know, like F7, for member 7, the axial stress is negative 1466.03 divided by 1 times 10 to the minus 4. And that is negative, I think that's 14,660,300, right? You're like, I don't know.
Yeah.
Okay, this is in pascals, or, you know, negative 14.6 megapascals. Member 6 is in tension, 1378.07 divided by 1 times 10 to the minus 4 gives 13.78 megapascals positive. Yes?
Shouldn't it be 14.7 megapascals?
Yes. I guess I meant to write that other 6. And then you can go on. Any questions about that besides why I didn't give you a cross-sectional area? It's all part of my master plan.
What's your master plan?
I don't know.
So then the maximum shear stress for each one is just that divided by 2?
That's right. Yep. That's right.
I have a question about
And the stress tensor would be like, you know, this stress tensor would be 13.78, zeros everywhere else. Yes?
for the joint assumption. So you either assume they're either all in tension or all in compression.
Yeah, just assume they're all in tension.
Okay.
And then otherwise you have weird negative assumptions and yeah. Also, if you assume they're all in tension, then the force values that come out match your sign convention for tension and compression, you know. So assume they're cables, but just remember you can get negative answers. Okay. Any other questions about that one or any other ones on this assignment?
I have number 6.
Oh yeah, number 6. So that's the one with the curve. Well, this is really, so really that's just kind of, the question is, what direction do you make, question?
This actually does have an answer. It's not labeled number 6 because the numbers.
Oh, okay.
It's exactly the same, it just has a different number.
Okay. Thank you. Great.
It's fine.
Well, I just want to say on this one that the tricky thing here is like, what's the direction of, if you call that diagonal member 1 and the curved member 2, what's the direction that you're assuming that tension force applies for member 2? You know, like, is it tangent to the, excuse me. And the answer is, think about the requirements of a two-force body. Ew. Okay, so a two-force body. Okay, so let's say that the body is this. Okay, and you have forces here and here, you know. What's required? So remember, the reason a two-force body, we know the directions of, or the line that those forces act along, is Newton's second law, in order for this to be in equilibrium, says they're equal and opposite. And Newton, the rotational equation, the moment equation, says for this to be in equilibrium, they have to be acting along a line. And so no matter what the shape of the body is, the directions of those forces are along that line. Okay. That's why that problem doesn't ask you for stresses and stuff like that for the curved body, because that calculation is complicated, but you do know the directions of the force. And so you can solve this problem just the same as if it was a member like this.
So in the circular one, it would be just straight up and straight down,
Yeah.
or something like that?
Exactly.
My initial thought would be it's two of them, like y and x at the same time.
Uh-huh. Right. So the way it is you're assuming this. And so let me make them straight. So if this is the pin A and this is the pin B, you have a F2 like that. And at pin B, you have an F2 like, no, I did that exactly wrong. Tension, so you're assuming, so you have an F2 like that and an F2 like that.
So for a weird body like that, would you say it's always pointing it towards its center of mass, or would you assume the center of mass to be?
Yeah, I think the easiest way is to think of replacing it with a straight thing and then do it like it's a straight thing. Yeah. Any other questions on those tension compression things? Or on trusses? Okay, well, let me finish the example problem I started last time. Okay, so we had this body. It started like this. And we figured out the external loads. So our full free body diagram is, we have a 2000 here. We still have these. And on the right side, we have a torque of 200 Newton meters and a downward force of 1,000. Okay, well, that all makes sense because of the symmetry of this thing. And so now we figured out that these are the three places that define the subfunctions, that define, where we have to make our cuts. So we have n equals 3, which means we have 2 cuts. This thing has a length of 2 meters. So cut 1 is going to be for x's between 0 and 1. So we have the 1,000, the 200. We haven't gotten to the roller yet. We haven't gotten to that 2,000. So the only other stuff we have is the internal loads. Okay, so Newton's second law says 0, negative 1,000 plus T negative V is equal to zeros. So that says that there's no internal tension. And V is equal to negative 1,000. And then we'll go to the moment equation about the x-axis, the long axis. We have negative 200 plus the torque is equal to 0. So the torque is positive 200. And then we'll do the moment equation about the z-axis. My about point, as always, is going to be on the left. So that 1,000 doesn't produce a moment. So all we have is the bending moment minus v times x is equal to 0. So m is equal to vx. And so m is equal to, our v was negative 1,000, so m is equal to negative 1,000 x. Yep.
When we're doing the moments, is it usually better to just break it into a separate one for each axis instead of
Since we're not doing y, I do it this way, because what would you write for the y components,
Will we be doing this with 3 moments?
We won't, no.
How would you represent the?
You'd have to be pushing out of the page.
How would you represent what?
How would we draw in a moment about the y-axis?
Yeah, the way, so if you were doing that, since all of this stuff is small deformations, you can assume everything is just, well, for the internal loads, that doesn't matter actually. How would you draw that? Well, you would draw it on a free body diagram as like a y component of a couple. And
Well, for it to rotate the y-axis, it'd have to be in or out of the page, right?
yeah, right. So the force, so if you had a force going like that, you know, then this would have to be counteracting that, the moment produced by that inward force or whatever.
You could probably draw it in like the XZ plane as opposed to the XY plane.
Yeah.
Yeah, well, so if it's just a matter of like, it's happening in a different plane than what you've drawn, then draw a different plane, that's right. If it's in addition to this, then yeah, you'd have to include a third equation that was the y component of the moments. And in that case, I guess probably the way you would want to do it is just write out the table and go through it that way, you know?
Yeah.
We have a quiz.
Oh, quiz, thank you.